All right, good day, everyone. Welcome back again to KodeCamp DevOps Bootcamp. Today, we are going to be talking about networking fundamentals in DevOps engineering. We have previously spoken about operating systems. We have gone through working with CI/CD and setting up pipelines and working with Git, our version control. Today, we are going to talk about networking, which would be how computers communicate with each other within a network. This is a very important stronghold, an important pillar when it comes to system engineering and infrastructure engineering. That includes everything from DevOps engineering to site reliability engineering to platform engineering to systems engineering, a bit of cybersecurity engineering as well, and many other things. So let's take a look at the content. Today we will speak on a brief introduction to what networking is and why it's going to be important for us as DevOps engineers. Then we'll move on to talking about some important standards that's enable the communication of computers with each other, which includes the OSI model, that's Open System Interconnection Model, and the TCP IP, which is a more recent version or a more recent model that is used today, apart from the OSI model. We will then go on to talking about IP networks, subnetting, and the CIDR notation. Then we'll talk briefly about routing and switching and DNS. This would be a good segue to learn about how networks work and importantly, how the internet works. This is part one. We'll treat part two in a later class. Where we'll talk more on some more advanced topics following up from this one. So very quickly, what is networking? Networking is the process of connecting computing devices together for the purpose of communication and sharing resources and services. The computers that you have working in the world today, for you to have access to resources, basically a good example is the public internet, right? Which is a connection of all computers. My computer right now is connected to your computer, and data is being transferred between these computers because they are connected to be able to share resources, which include this file, this data that I'm sharing, is a form of communication between our two computers. There are some cases where you can use the CPU of a computer or the storage of a computer that is located remotely from the computer. That connection and that sharing of that resource is done over a network. And that connection is what we know as networking. And in DevOps, primarily, when we look at networking, we're looking at how we manage, how we configure, how we provision, which means to set up networks, how to automate some processes on networks so that we don't have to do everything manually, and how to deploy infrastructure and services over networks. And this would cover everything from making networks and network connections between computers as reliable as possible. It will include working with secure practices, setting up security, so that to keep out attackers from getting access to our data and our resources through our networks, preserving important resources and critical private resources that we have on our network, and ensuring that security, creating a system of effective communication between all our devices and all the components of our infrastructure system, which could include our applications, our servers, our databases, right? Different tools that we have, in our networks. Okay. All right, moving on quickly to the OSI model. The OSI model is it's a model that was created, I think, like maybe in the 1980s. It's a standard by which computers are able to communicate over a network, right? It has different layers that data passes through in order to move from one computer to the other. It first begins from the application layer. The application layer is the layer where you have human interfaces, human interactions, contains protocols that allow for softwares to be able to send and receive informations with meaningful data that users can understand and interact with. Some of the protocols, like you might know, include the hypertext transfer protocol, which is an example, an easy example for which internets and transfer of data and receive of data over the internet works, with HTTP and the secure form, which is HTTPS. So enabling that end user interface for applications and users to communicate across is at the application layer. After the data gets from the application layer, it now goes into the presentation layer, which the presentation layer is the layer that prepares data for the application layer. It's goes through this is the layer where things such as encoding data, if your data is private data, right, secure data, and needs some form of encoding before it's moved to the application layer, or so some form of encryption before it's moved to the application layer. This is the layer at which is done, at presentation layer, which includes processes and protocols by which the data that you're working with, the data packets that you're working with and you're sending over your network is prepared for presentation, which includes encoding, encryption, maybe compression, and things such as that. The next layer is the session layer. This is where communication happens, creation of sessions. A session between on a network. When you talk about session, it's an open channel of communication between devices, by which data can be transferred, right? So the layer where sessions are created and sessions are maintained that ensure the data to be transferred and at the end of its transfers to be closed, right? Opening and closing of sessions and channels of communications between devices for communication is done at the session layer. Now, the transport layer is a layer that takes data from the session layer after it has been transferred and creates segments out of it. And the segments, this layer is responsible for assembling segments or breaking down segments into smaller packets that can now be sent to the network, to the networking layer. Things such as flow control, connection, bitrate, error control is done at this layer, the transport layer, which is responsible for all the forwarding routes, all the reliable transfer of services between the layers. We've talked about the session layer, presentation layer, and the application layer. These are more of the software and logical parts of the OSI model. The next one, the network layer, the data link layer and the physical layer are more of the physical components of the OSI model. The network layer has the function of receiving packets from the transport layer, reassembling them, because the transport layer would break down the data into segments. So assembling them back and routing the packets to the physical layer. That's the purpose of the network layer. It performs a function of routing packets to the destinations when received from the transport layer. The data link layer then establishes communications between physical components, physical nodes, right? Physical components of the network. It works with various protocols on a physical layer. That's how you have the application layer for more human readable communication. You have the data link layer that is more concerned with communications between physical devices and physical networks. Working with things like the MAC addresses of various components and various nodes on the network and transmitting data between them. And finally, the physical link layer refers to the physical cables and the physical connections and physical connections that are set up within our network. Okay, so that's the OSI model. We have when data is received, application from the physical layer or being sent. When the data is received, either from the application layer is being sent from the physical layer. Depending on whether it's a receiving server or a client, right? You have it from the application layer and goes down to the presentation layer, to the session layer, to the transport network layer, data link layer, and then to the physical layer. Okay. So this model, out of it was now created a more modern model that most of the components in our networks today work on, which is the TCP and IP model. This has just 4 layers, which when compared to the OSI model might be an integration of 1 or more layers from the OSI model. For instance, the application layer performs the function of the application layer in the OSI model, the presentation layer and the session layer. And then we have the transport layer, the network layer, and the network access layer from on the TCP IP model. Okay. So speaking to the TCP IP model of network communication specifically, it's a set of protocols that are used by the internet and other networks, maybe your personal private virtual network that you work with, or your local area network. So this TCP IP is used by these networks, and it has 2 major protocols, which includes the transmission control protocol, which primarily performs at the transport layer, and the internet protocol as well. The that TCP IP separation creates 4 sections and 4 layers that correspond to the major layers of the OSI model, as we saw in this diagram. So the network interface layer, which is also the network access layer here, that's responsible for the physical transmission of data over the network medium. things like the Ethernet cables, this your physical connections, Ethernet cables, wireless connections, addressing resource protocols, which resolves IP addresses, which are the addresses of your resources on the internet, to the MAC addresses, which are the addresses of your computers on your network, your specific computers. So you have your IP address, which gives the address, the location on a network, and the MAC address, which is the address of a particular host within a network. Okay. These are two important differences that you have to know: IP address and the MAC address. So Ethernet, the wireless, the physical connections and the physical components for data transfer within your TCP/IP model happens at the network access layer. Then we have the internet layer that handles the movement of packets within your network. Things like routing, addressing, packet forwarding, and works with the internet protocol. The internet protocol, like I said here, is the main protocol responsible for delivering packets from the source to the host destination using IP addresses. So it delivers, it's the main protocol, the main sets of processes, right? The internet protocol that is used to deliver data from one network to another network. And this, using the IP addresses. The IP addresses are like a representation address, an identifier of a network within of a network, right? And there are two ways to specify IP addresses. You can use the IPv4. That was the first notation of IP addresses, which is just 32 bits, and there's a much a longer one, 128 bits address, which is the IP version 6. Basically IP version 4, it's, I think the standard organizations have decided that we are overutilizing the IP version 6, so they're encouraging more use of IP version 6 for setting up your IP addresses within the network. We also have the ICMP, Internet Control Message Protocol, which is used for diagnosing networks. This refers to when you're using things like ping, you're working on the ICMP protocol to detect network errors, do some liveness probes on networks and see if they are up and live. Okay. So to the transport layer of the TCP/IP, the transport layer, this provides the end user communication services for applications and ensures that data is transferred reliably and accurately. The protocols we have here are the TCP protocol, which is a transmission control protocol, the UDP, and a combination of both of them. The TCP protocol is a more connection-oriented protocol, which ensures reliable transfer of data. When you use the TCP protocol, you want to ensure that all packets get from the source to the destination, every single packet. But a more low latency connection, you have the UDP, where you have things that's where you don't need it to be as reliable, and ensure that you don't need to ensure that every packet gets to the destination, right? So if you're sending something like a video call, for instance, you don't want to ensure that, you don't necessarily want to ensure that every single packet gets from source to destination. right? That's why sometimes you can see that your video call can have a low quality or a higher quality. And the higher the quality, um, the more packets have been sent and received from source to destination, that is from server to client, right? And of course, the stream control transmission protocol, which combines both the TCP and the UDP protocol. It ensures higher reliability, and it's a more message-oriented protocol and a more oriented form of communication. So on the transport layer, you have TCP, UDP, and the SCP. Okay, a quick depiction of how TCP looks. TCP, for data to be sent, the two clients have to acknowledge, you you have to have a handshake, this three-way handshake, that's what this is called, to ensure that the two resources are available for the connection. So the client first sends a synchronization segment to the server, and the server now has to respond with a synchronization acknowledgement that is acknowledging that yes, it's alive and ready to begin the communication. And then this client also has to respond again that it's acknowledges that the server is up. So this would ensure that both clients and server are up and ready for the communication, and it creates a more reliable transfer than a UDP connection, UDP transfer, which just where the sender just where the client makes a request and the server sends the response. There is no prior handshake or acknowledgement, so some data packets can be lost here with UDP. But this form of connection and transfer of data is usually used when you don't necessarily need for the communication or the packet sense. You just need a communication between the client and server, requests and response. Okay, and finally the application layer, which is the last layer of the TCP. You have the application layer, which of course has the end user and application specific functionalities where you can have a more human readable form of connection and communication. So the application layer contains protocols and services that directly interact with end users, like two software, two computers, and provides application specific functionality. So here you have protocols such as the hypertext transfer protocol, which is used for the transfer of web pages and various connections over the internet, right? Then you have file transfer protocol. You have many other protocols on the application layer, SMTP, SSH, DNS, and a lot more. Okay, so now that we've spoken about the various models that networks use for communication, let's talk about how networks are created and designed. We are going to look at the concept of subnetting, which is a technique of dividing or breaking down a larger network into smaller, more manageable subnetworks, smaller networks that provide for isolation within your own network. Isolation within your network. This isolation has the primary purpose of efficiency in managing communication, managing resources, and also security, right? So you don't have to create a network. If you have a network, you can break it down into smaller networks and create certain resources and certain subnets that can be isolated from other resources and the public internet as well, right? So here you have a depiction of a network, a large network, maybe my network, for instance, and I can then break that down to um, some public subnets and some private subnets, depending on how I want to design my network. Some of the benefits of subnetting, you have that it improves network security, right? It enhances the security of a network that you create by enabling teams to isolate resources and isolate sensitive services into subnets, and then give those subnets limited access. Say I have a database that contains sensitive information of my customers, right? And I also have a front-end service, a front-end server, right? I need users to be able to connect to my front-end server, but I don't want users to be able to connect to my database, for instance, right? So this is where subnetting comes in, and it's now important. So I can keep my front-end server in a subnet where users can have access to it, but the database will sit in a subnet where users will not have access to it. However, the front-end server, which needs data from the database, will have access to that subnet, right? So that's just a method of creating an isolation, limiting access, and um, giving more security to different sensitive resources. The next benefits of subnetting as a process is the efficient allocation of IP addresses. So to avoid wasting IPs in a network, you can create smaller networks that will have their own IPs that you can now more easily allocate and manage within that subnet, right? Breaking down your network is important for creating a better system of managing your IP addresses within your network. And it also improves the performance of networks because you can now reduce congestion within your network by creating different smaller networks that can now work with specifically. Now, when you have a network, there are methods by which you create that, by which IP addresses are created for your networks and different resources within your network, right? So an IP address and a subnet IP address, the IP address of a subnet will contain the subnet mask. It will contain the network ID, which will be a portion of your IP address. When you see the IP address, there will be a portion which will tell you that this IP belongs to this network, right? And then there will be a particular part of the IP address which will specify the hosts. That is when the host is the particular resource that has the IP. Then for the entire network, naming it, you have the side annotation by which you can assign a value to an IP address, which will tell you how many resources that can be allocated to that subnet, right? Okay, so your subnet mask is a 32-bit number that represents the IP address of your network as a combination of both your hosts your host ID and your network ID. And it's used to determine which part of your IP address refers to the network and which part refers to the individual device or the individual resource or the individual computer or computing um, device on that network or within that network. I think I'll need to do some diagrams to explain this better, but let's go ahead. The binary here we will use binary notation. You can use a binary notation or you can use a decimal notation to create the subnet mask, right? So the subnet mask should consist of ones and zeros. When you're working with the binary representation of a subnet mask, it consists of ones and zeros, where the zeros, the ones will represent the network, right? It represents the network portion of the IP address, and the zeros represents the host portion of that IP address. If you're working with a decimal representation of your subnet mask, if you're writing your subnet mask as with the decimal representation, you use 255. So where you have 255, that's particular octets, right, would be part of the network portion of your subnets. Okay. So if I have 255.255.255.0, I'll know that this 255.255.255 is the network portion. And that zero can now refer to the particular host on that network, right? Okay. So let's look at the network ID. So the network ID is a portion of the IP address which identifies the specific network to which the device belongs. When you perform an AND operation, a bitwise AND operation between the IP address and the subnet mask, you get the network ID. So routers use the network ID to determine the destination, to determine the network to which they are sending packets to, right? And the host bit of the IP address would be a set of zeros when calculating the network ID. So looking at this example, for instance, you have an IP address 192.168.1.10, right? That IP address having a subnet mask of 255.255.255.0 shows here that the host bits are set to 0. So your network ID is 192.168.1.0. That is the network ID to which this IP address belongs. In that network, you have a specific host, a specific device within that network that has the IP address of 192.168.1.0. You can have another device within that same network that will have the IP address of 192.168.1.2, for instance. You can have another one that can have 192.168.1.4, for example, right? So if you're working within a subnet, for instance, and that subnet, that's entire network would have an IP address, so that when routers are sending data, right, from one network to another, they would know specifically what network they're sending that data to. And they will know that the network I'm sending to, based on the subnet mask, the network I'm sending this data, this packet to, is 192.168.1.0. When the data packet gets to that network, say there's a switch within that network now. it's to know that the specific device that I'm sending this packet to, the specific device that this packet is being sent to is 192.168.1.10. So it doesn't just send it to the network and just drop it in any random devices and drop it in any around to any random device's IP. It's important to know the network and the particular host. Now the host ID is now the portion of the IP address that identifies a specific device within that network. It is basically the remainder of the IP address after you've used your subnet mask. Where you've used your subnet mask, right, to derive the network ID. The remaining part of the IP address will be your host ID. Okay, so we have this IP address again. Say the IP address is 192.168.1.10. And you have your subnet mask, which is 225.225.225.0. And you have the host bits set to 0. That's the last octet there, set to 0. Then you know that your host ID is 10 within the network of 192.168.1.0. Okay. Okay. I think I will go on and I'll come back to this later if need be to do some more illustrations using diagrams. Okay, so speaking to CIDR notation now, which is a method of representing the subnet mask, this 225 that we have here, of representing the subnet mask by using a slash and a number after the IP address. Okay, to represent the subnet mask of the network. So if you have, for example, if you have this same IP address, 192.168.1.0, the CIDR notation brings in this /24, which tells you that if this is converted to the IP address, you would have the last octet. You have the last octet as your host ID. How this works is that your IP address given to you as a numerical value, as a decimal value, 192.168.1.0 can also be represented, in fact, to the, as you know, computers communicate with binary. When converted to a binary format, you have a 32-bit string, a 32-bit numerical value. This is when working with IP version 4. You have a 32-bit numerical value. This 32-bit numerical value is broken into sections of 8, which is an octet. So you have your first octet, you have your second octet, you have your third octet, and you have your fourth octet. If you convert each of these different octets into their decimal values, you would get your IP address, right? And for the CIDR notation, the CIDR notation is the numerical value minus the CIDR notation will give you the portion of the IP that's would be in 0. So if I do 32 minus 24, for instance, I'll get the value of 8. And you see there that we have 8 zeros in the network. So showing how this is important. So considering the IP that we just looked at now, you have a network prefix that's /24 of 24 bits used to depict the network parts, to show you the network parts of that IP address. And the host portion will be the 32, which is the value of an IP address in IP version 4 notation. You have IP which has 32 bits, which is 32 binary characters. So if I have /24, for instance, I know that the /24 represents the network portion of my IP address, and 32 minus that 24, which is 8, represents the host portions of the IP address, which can be used for to determine any difference hosts within that network. Okay. So now a way to determine the number of hosts that will be on in a network, say in your sub network, you work with raising the value of the host portion, raising 2 to the value of the host portion will give you a number of available addresses for the hosts, right? So if you have this IP address of 192.168.1.0, you have your host portion as eight values. If you do 2 raised to the power of 8 and get 256, you know that within that network, within that sub network, or within that network, you have 256 available IP addresses that can be assigned to hosts, right? Okay. Now, within a network, breaking it down into 2 subnets, for instance. Let's come back to the description of a network and how the subnets, the CIDR notation works for breaking down a subnet into networks. Okay. So we'll come right back to that. Moving on to routing and switching now. Routing in a network is the process of specifying the path along which data packets within the network are sent. So you have a route that operates on the network layer within a network, and it's responsible for the process of sending packets from one network to another, right? This works with using the IP address of various networks. So when you send a packet on the network, you send it from a source IP and you have a destination IP. So routing is a process by which data is sent from one network to another network. Switching, on the other hand, within a network is a process of forwarding data to specific devices on the network. This one now works with the MAC address of different components of the network. So switching is the process of forwarding data frames within the same network. Primarily operates using the data link layer of the OSI model and sends data from one resource, one host within a network to another. Okay. So routing uses the IP addresses of networks, and switching uses the MAC addresses. Now, these are just some examples of network routers and network switches. And we have the description of how the flow looks like. So from the internet, say from maybe the application layer, you have data or data frame sent to router, and the router would route it to a particular network. And you have your switch that would send that data traffic to various computers or various resources within the network. To further look into communication on networks, we will speak on ports and protocols. Okay, so protocols are the standards. We're speaking about protocols. We talked about some protocols and various layers we perform on. So protocols are standards. It's and sets of rules, standards that define how data is transmitted over a network. Different devices with different configurations, different OSs. The protocols ensure that devices can communicate with each other. When they're in the same network, they can communicate with each other through the various, when they meet various standards and the various rules defined within a protocol. Some common ports that we know are the HTTP protocol, some common protocols. The HTTP protocol, which works with port 80. We have the SMTP protocol. We have SSH protocol. We have some things like MySQL and Postgres protocol that helps with database communication. So protocols specifically, they work to set standards of communication. They define data formats, they define how data exchange should be done over a network when sending a particular type of communication or a particular type of data, right? And they perform, depending on the type of protocol, perform on different layers on the OS side or TCP model and handle a specific type of communication, right? If I want to send a specific type of communication, say I want to send a web page, web traffic, right? Over an unsecure network. That type of communication will be different from how the data, the rules and the formats the data will be sent over a secure network, right? The formats, the representation of how data is sent over HTTP will be different from how it is sent over secure HTTP, right? Secure HTTP, that is HTTPS, would need some more encryption and more security. And that will be defined with the protocol of HTTPS. It will be different from the protocol of HTTP. And speaking to different ports, different standard ports on your computer and within your network. Okay, so it's just some layers and of the OSI model and the protocols that perform on them. So you have on the application layer, you see that the end user forms of communication perform with these kinds of protocols. Some of the common protocols that they perform with the HTTP protocol, FTP, SMTP, work on this layer 7 protocol. On layer 4, that we now have that is the transport layer. We now have things like the TCP and UDP, which are some other protocols, some other standards, right, used for transporting data and transmitting data, right? You have the TCP, which we spoke about later on, which is a more reliable, connection-oriented and reliable form of data transmission and transportation. And then UDP, which is more connectionless and lightweight, but faster. You also have the IP protocol on your network layer, and you have your Ethernet protocols on your data link layer, right? So different protocols perform and set the standards of communication on different layers and different layers of your networking model, right? In this case, your OSI model. Okay. So that's ports and protocols. Ports, on the other hand, these are protocols. Ports, on the other hand, are the open channels on a system where communications can happen, right? You have a specific channel that's open for communication based on the type of data that is being sent to that and being received on that, right? Different protocols specify different ports for their communication, which within your own environment, you can decide to set on your own. Okay, so quickly looking at DNS, which is the domain name system, right? You will notice that within your use of the internet, and if you've worked in a more a more private network, but taking the internet for instance, we know that different web pages have different addresses, but we don't need to remember the IP addresses of these different networks, right? We have specific names for you. Maybe we use www.google.com. But that www.google.com is not the IP address of that server that you're communicating with, for instance. The job of the domain name system is to translate human readable text, for instance, www.google.com, into the IP addresses of different servers, right? So you have a domain name server, a DNS server, which does that translation for you, so you can remember the human readable form of that name, and that is now translated into the IP address of the resource that you're trying to communicate with. Okay, so the domain name system, DNS, is a hierarchical and decentralized naming system used to translate human readable domain names. That is your www.google.com, www.KodeCamp.com, for instance, into IP addresses that computers use to identify each other, right, over a network. This allows users to have access to websites without having to memorize or remember the specific IP addresses of these websites. When we say a decentralized system, okay, we're speaking to the fact that the DNS as a system doesn't belong to a single person. There's no single organization that sits down and manages all the DNS names that we use over the internet. There's no single control by of the entire system by a single entity. So there's no single that single point of control doesn't exist. DNS as a system is managed by multiple entities, right? Various organizations, various companies have the rights to manage and create domain names and store domain names for access over the internet. So I can decide to create my domain name using Cloudflare, right? You can decide to create your own using maybe Google, Google, Google domains, right? So different organizations and different entities uh, have and maintain domain names, right? And these exist across multiple servers. You have a single server where domain names are kept and stored and does the translation. It's a distributed system, a distributed server around the world. And this allows for the removal of a single point of failure, right? So that if something, for instance, happens to a domain name server, it will not affect the entire world because there are various multiple systems that handle that. I think within your own organization, you can have a private domain name server system within your private network that does the translation and the translation for you of various domain names into IP addresses. Now, we said the domain name system is a hierarchical and decentralized system. You know what the decentralized is? No single point of control, multiple servers, autonomy, right? You say that each domain name, each subdomain is managed by a different organization, right? Different organizations manage different domains. So that's autonomy and fault tolerance, and there's no single point of failure on domain name systems, right? That's the decentralized property of the domain name system. There's also the hierarchical, which you might be more familiar with, right? The DNS has the root servers, right? Is the hierarchical structure, the hierarchical different levels of how the domain name system is set up, with each level having its own children and its own children and its own children until it gets to your name. And the translation then happens between these various levels, right? So using these various levels of this hierarchy, right, let's try and understand how the domain name system works, right? Say a user types in www.cisco.com, or this is www.bbc.co.uk, for instance. Within your system, DNS first checks if you have that, if you have a storage of that IP address on your system. Say maybe you have visited www.google.com many times on your system. There will be some storage of what's the IP address of that DNS, that domain name is. So translation of that will be easy. If it's not found within the system, the system then queries the root name server of that domain name, right? Which should be the .com, right? It starts from that .com to do the translation of your DNS. So you have www.cisco.com. The .com, your top level domain, it does the translation, it gets that server, say this one, this .com. Then from the root server, the root server then responds with the address, the IP address of your top level domain, which will be your .com or your .uk, right? From the top level domain, then resolves the authoritative name server for that domain. That authoritative name server would be your Cisco, for instance, which would no, the Cisco would be like the second level domain, right? Which represents your own server. Say if I have www.malco.com, you have .com, which represents a particular IP. After it translates that, it translates the next level, which will be the Malkiel. It does that translation, then of course it does the translation for the World Wide Web. So that's hierarchical breakdown of the name from the .com to the second level, if there be .co, or to the authoritative name of your server, Cisco or market.com, and breaks that down and finally takes it down to resolves it to the main IP of your server. That's how the DNS flow works with a hierarchical structure. Okay. Okay, so DNS has the hierarchical structure of DNS starts from the root level, which should be the top hierarchy of your root server, which holds the information of your TLD, right? So like .com, your root server will hold the information, that is the how you can resolve that .com TLD. And when you resolve that TLD, you go from the root level to that TLD, which now holds the information about the domain that has been registered with that TLD. For instance, if you have malkill.com or you have KodeCamp.com, after it resolves your .com from the root level, it resolves, the DNS resolves your .com to a particular .com server. That .com server would hold the information and the domain translation for your KodeCamp. And when it does that KodeCamp, if there's a second level, it goes to that as well. And then down to the subdomain, which is your www. If you have that as parts, or your specific subdomain for that's that's level of the hierarchy of your DNS. Okay. So, like I explained, you have your DNS, which how it works with the hierarchical flow. You have a user that first does a query for a particular domain name, and the DNS now has a job of translating that domain name into an IP address. So then it begins from the root server, which responds with the IP address of .com, the top level domain. After that response to .com, it then responds if there is a second level, maybe if you have something like UK as your TLD, and you have co, and you have something like bbc.co.uk. The co.uk, you have the UK as your top level domain, you have co as your second level domain, then you have the authoritative server, which is your the domain that you register. Maybe that is like a specific name, codecamp.com or the myname.com or example.com, for instance, which is referred to as your authoritative name or your authoritative server. This is registered with the top level domain or the second level domain, depending on how your hierarchy is configured. And then you have your subdomain. Sometimes you can have like info.codecamp.com, you can have mail.codecamp.com, you can have support.codecamp.com. Those info supports www.mail. Those are all your sub-level domains, and that has its own resolve into the by the DNS. Okay. Okay, so moving on to the different kind of records that are on our domain name server. You have there are different types of records. When you create a record will be like translation. When you're registering the translation of your domain name, if I'm doing codecamp.com, should go to this particular address. That's record. The domain name, and what it should be resolved to. That's what a record is like, right? So if I'm registering my domain name, I'm registering something like KodeCamp.com. I would register, I will create a record to register KodeCamp and resolve it to my server IP address, which is 192.168. Dot 10.0 or dot 10.10, for instance. That record is known as a DNS record, and that's what I would create as my domain name record. Okay, so you have an A record, which maps a domain name to an IP address. That's like the simplest form of record that you can have. That's like the simplest form of record that you can have on your DNS. You also have your still on the A record, which maps your name to your IP address, but using the version 6, the IP version 6. This is created using an A record. You also have a canonical name record, which maps the name of a canonical name, right, to the true name of a domain. So if I have something like example.com maps to a specific IP address, and I want to map a different name to that example.com, for instance, I'll use a CNAME record, right, which can map maybe www.example.com. Use a CNAME to map it to example.com. So that's when you go to www.example.com, you will still get the same response as when you go to example.com, for instance. You also have an MX record, which is used for a mail exchange that specifies the mail server responsible for receiving mails on your behalf, on behalf of the domain, right? If you have a mail server, a mailing server within your network, there's also the TX record, which just stores text that can be used for verification of security and things like that. Then you have the name server record, specifies the authoritative DNS for your server, and also the PTR network, which is the pointer network, that maps an IP address to your domain name, which is like the reverse of what you have in A record. There are many other records. There's an SOA record. There's many other records that you can use with your domain to perform the mapping and record the translation from IP from domain name to your IP. Okay, so I think we can take some questions now. I know there will be a lot of questions. I can try to breeze through the foundations of this. So we'll go into some practical descriptions, right? Using diagrams later on. So are there any questions? Or should we just go into you can just put up your hand or drop it in the chat box. Okay, so I think I'm hearing that we should just move on to hands-on. Okay, so I'm going to share my screen a little bit. Okay, so we have here a network, right? We have a network. We're looking at subnetting, right? For instance, taking it from subnetting. We have a network. We have two subnets, and then we have a server within one of the subnets. Okay. So now we need um addresses for these various networks. So your network, for instance, will have its address. The entire network will have an address. Then you have different subnets within your networks, which will have their own addresses as well. Right. Let's look at this for instance. This as a machine within your network. So you have another machine within this other network. Okay. So you have this server here, which will have its IP address. You have a subnet, which have its own IP address, and this other subnet which have its own IP address, still within this network. Okay. And then the various servers will have their own addresses as well. Now, taking this for instance, okay. Look at this IP for instance. Right? Or let's use the one we've been working with. Think from the 192.168.1.10. Okay. Let's use that IP address for our network. So a subnet mask will tell you the portion of this IP address which belongs to the network, which specifies the network, and the portion which would talk about the hosts in the network, right? Which would be right now in this case your subnets. So say we have a subnet mask of for instance, right? Now this you're seeing that it's breaking down your IP address into the portion for the IP and portion for your subnets. Let's say we use Yes. Over 255. That's 1, 2, 3, 4, 4. Looking at this with the subnet mask, right? It's just a conversion from this 255.255.0.0 into decimals that will give you this. And from this, right, you can see that our subnets is showing the portion for the network itself, which is the 192.168, and the portion which we have here for the hosts on the network, which will be these 0 parts. Okay. That now gives us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Is that correct? 5, 6. This is meant to be an octet. An octet 1, 2, 3, 4, 5, 6, 7, 8. An octet with 8 characters. 1, 2, 3, 4, 5, 6, 7, 8. So 8 characters there. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. So we have it complete. We have our octet complete. Directly looking at the octets now, we can see 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Those are 16 characters, right? 16 characters available for the host portion of the IP. And you have your subnet mask, where you have your network portion of the IP, which ones for the 192.168. 16 here would now give us, if we put /16, right? This has represented the subnet mask. It has represented the subnet mask by using your CIDR notation, right? If this is what you're given and you want to convert it down to your subnet mask, I can just do your and just sort of spread it out and see that you have 16 values for your 0, and your 1, which is the network portion part of the subnet, starts after you've completed those values. Say I have let me see 20, if it's 22, for instance. I think we had 24 before. So we have 20, right? We have 16 bits. That's 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For instance, I'll put this. Okay. If I convert this to decimal now, right? I'm using a decimal converter here. I'm not writing it on my own, just to be clear. So that is can we see my screen? We have 1, 1, 1, 1, 1, 2, 3, 4, 5, 6. That's 6. So you can have as your subnet mask, for instance, for /22. Okay. So I'm looking at the charts. Is that portion clear? Let me go right back to 255. Yes. So side annotation, how you can specify the subnet masking using side annotation. Okay. Let's try to explain it again in a different way, since it's not clear. Let me reduce this. I'll put 1 here for example. So we have a subnet with the notation of 192.168.1.0 /24, for instance. Okay. Now this, as you're looking at it, we know we need some values. There's a subnet mask which tells you what portion of your IP is your network ID, telling you that, okay, this IP is directing you to this particular network, and your host's ID, right? Which now tell you, okay, in this network, this particular host, okay? And you have, say, a host of 192.168.1.12. Okay, this right here is what is it? It is server A. This is server A. Let me go in here, I'll tell you. So we have server A and we have server B. Okay. Now, this IP address is server A. Okay. We have 192.168.1.0/24. This IP has this IP2, right? It has a network portion, for instance, which tells us the particular network it belongs to. Okay. It has a host portion, which will now tell us the particular host that owns this IP address. What divides it into the network portion and the host portion, the host ID, the network ID and the host ID. What divides this IP into network ID, host ID is your subnet mask, which is basically ones and zeros. Okay, so your continuous ones will show you the network portion of this IP, the network ID portion of your network address. Have 15, right? Equally as an address to a house. Okay. 15 Obafemi Awolowo Street is the ID of the street. Okay, let me see. Let's say it's like this, right? Obafemi Awolowo Street is the ID of your street. Ikoyi is the ID of a city, right? In this city, there's a street. This is the street ID. And there's a house. This is the number of the house, number 15, right? So we have a street ID, the network ID, and you have a particular host inside the network as number 15, in this case, number 12, which represents that particular host on your network. How do you determine which part of this ID? Say you don't have any comma, for instance, you just have it like this. How do you determine which part is the network ID, which part is the host ID? You have a subnet mask, which could be represented either in the binary form or the decimal form. Now, if you have a mask of, you can have a mask of 255.255 dot what? Try this. Okay. If I convert 255 to decimals, okay, let's use okay. Or you want us to solve it manually? No, thank you. You can solve it manually, but then what to use the use of the internet? Let's see, we have one from Geek for Geek. This is true. So let's use this one. So binary to decimal, let's try decimal to binary, for instance. So if I do 255, right, and I convert, that's one decimal here. Switch for this to change to 10. Let's move on. So we have 255 here. If I convert 255 to binary, I will get this number here, right? I don't take this step by step. If I convert 255 to binary, okay. So if I convert 255, convert it to binary, from decimal to binary, and I convert, I'll get this number. So I'll take this number and I'll put it here, right? 255 again. We have the same number. We have 138. Okay. 138. Let's see what we get. Converting 138. Okay, let's get this number. We have, and then finally, if I convert 0 to from binary to decimal, I'll still get 0, for instance. Okay. So get now This is a good subnet mask. This is a good subnet mask. Give me, you have to use either 255 or 0. You can use this kind of number. Because you need continuous ones or continuous zeros. So I don't think you ever see a number like this for a subnet mask. So let me put 0 here. Right? Let's now work with that. So you use continuous ones or continuous zeros to determine your subnet mask, for instance. Okay. So you have 255.1.1.1.1. Right, to mask this and this other mask. So when you have continuous ones, continuous zeros, you know that portion, continuous ones, that portion is your network mask, your network ID, and then you have a portion as your host's ID. Okay, so that's what we are doing right here. We have this, okay, we have 192.168.1.24. Okay, as a CIDR notation. Okay, CIDR notation just is a way of writing your notation without using this 255. Okay, it's a way of specifying your subnet mask using a suffix, right? This /24 slash number. How does this specify your subnet mask? If you do, you know that you have your subnets, your IP. It's a 32 bits numerical value. 32 bits in the sense that it has 32 characters when it's written in binary. If you count this 0, it's 32 characters that are available to you. 4 octets, octet 1, octet 2, octet 3, octet 4. 4 octets giving you your 32 bits. Yeah, 4 times 8. We give you your 32 bits. So if I do that 32 bits minus my CIDR suffix here, it's 24. I'll get the number for my hosts, right? If I come from this part, right? I come with I'm getting the values for my hosts, right? So I come with 0. So there's 0, 0, 0, 0, 0, 8 zeros, right? So that host is complete. I can now have the ones because I know that these parts are maxed out for my network. Okay. That is 24. What if I have 26, for instance? Okay. What would that give me? So I have this kind of subnet mask. Yeah. But 6 zeros, right? So this is the portion that should be for my host's values. If I put this across an IP address, for instance, this is just a mask for it. If I put it across an IP address, I will see that this portion of the IP address, right, these zeros, can be changed for like this one, for instance. This 0 here is the value for my host /24. Let me take this out. This value for my hosts, right? So how many hosts can go in here? Okay. If I do two, three raised to the power of 22 minus 24. Right. Oh, what I give me? I'm going 2 raised to the power 8. That's what? 256. So I have 256 possible host values. So I can have from 192, that's 168, that's 1 and 0. What this will translate to, that I can have from possible values between 8 and 0. Okay. The thing is, obviously, there are some reserved IPs for broadcast, for things like that. So you might not have all the full 56 to assign to your resources and your different computers and components and your network. But there are 256 possible hosts that you can get from this network. Okay. Does that calculation make sense? You can go over it again. But let's go on to break down this network. Okay. All right. So let's go on to break down this network. Um, 192, that's 168 slash 24 gives us 256 possible hosts. But we want to break this down into a network now. So we want to break it into sort of 6 hosts. Okay. So we have two networks here, right? Um, Out of this network, we can break these two networks down into, for instance, if we want to break it into 192.168.0 slash dash 26. Okay. And we want to give this other one the side out of um, what I'm thinking of now is to make sure that we avoid conflict between these two networks. Because inside this network, you're creating two sub networks, right? So you need to make sure that an IP that's is created in this network doesn't get created in this other network. Okay. So say we give this, and your network address is 192.168.1.0. Okay. And you have 192.168.1.0 slash 26 here. Where you have this one ending would be okay. So let's see what you go into here, right? We have this free number here. For instance, let's put X there. Let's put X there. Right. So with this 26 now, what I'm having is 192.168.1 slash 26. I will do my 32 minus 26, which will give me 6. Okay. So I have 6 here. That's 6. Is my number, is the number for my hosts, the zeros for my hosts, right? I think we got it last time. Gave us like 6 zeros. Okay. Using 2 raised to the power of 32 minus 26 would give us 2 raised to the power of 6. 2 raised to the power of 6, that is 64. We have 64 hosts that can be in this network, for instance. That should be from 192. Let's do that now. 192.168.1. That's 1, 2. For instance, that is not regarding the that's not regarding the reserved IPs, right? So you have some reserved IPs for broadcasting and some other things. So this would be the range of IPs for hosts within this subnet A, right? And we will have this guy as one of them. Okay. So between 1 and 64. From this one, say we start from for instance, to have IPs still /26. You will get something like maybe 65 to starting from 0 here. Okay. Say this subnet now starts from 64 to 128. For instance. And so that is 64 hosts inside here. 64 hosts in this subnet. Another 64 in this subnet. Okay. And the entire network itself is able to accept 256 hosts. So you still have the ability within this network to create 1 or 2 more subnets inside with this same side annotation of /56, which will give us 64 hosts. They will create subnet C and subnet D. Even with the same 64 hosts, you can still utilize all this. So with that, I have now been able to separate all these IPs from this to this inside this subnet, right? And I can decide that these IPs should not be accessible except the request is coming from a particular IP, right? For instance, I can decide to make this okay. First of all, do we understand what we've just done? Let me do it. Do you understand what we've just done here? Yeah. I'm still here if anybody doesn't understand. Hello. The side calculation we did, who doesn't understand it? Okay, so I think we've been able to explain. We can go into practically building out a network and dividing the subnets in our next class. But we've been able to practically explain how you can build a network and create subnets from it, right? Using side annotations and knowing your network ID and your host ID. Okay. So thank you so much for joining the class. I hope to see you next time where we can do this practically. Thank you once again. Goodbye.
Thank you, sir. Good night, sir.
Nice.